I want to welcome you to another motivated statistic class. Of course, today the focus is going to be on matrix decomposition. Uh, Earlier in the week, I I introduced you to linear algebra. So one of concepts in linear algebra is matrix decomposition. So why um, are we what is the essence of this, like studying matrix or decomposition? It's because um, when you are working with motivated data set, the motivated data set is complicated, and if your intention is to maybe reduce the dimensionality in the data set. Of course, the approach that we use that I'm still going to walk you through in this course that we call the principal component analysis, the canonical correlation, some of them actually rely on matrix decomposition. So number two reason why matrix decomposition is very, very crucial is because, if we are able to split matrix into smaller pieces, I want to believe that we simplify complexity. Okay, it will enable us to have an understanding of the data structure. Okay, by way of decomposing the matrix. Then I'm also going to say matrix decomposition supports multivariate modeling. As time goes on, I'm going to walk you through some multivariate modeling, like multivariate regression, like multivariate analysis of variance, like classification and so on, like that. All of that. You we can moving forward. Of course, the idea of a matrix decomposition becomes very, very essential. So we don't just do what we do. There's a reason why we do what we do. So because of the fact that the matrix decomposition is most of the techniques that we use in actualizing our aim and our intention in the multivariate world, of course, rely those techniques relies on matrix decomposition, and that is the reason why we need to be able to get ourselves familiar with the fundamental principle of decomposing matrix. Okay, now I think I've just justified why matrix decomposition. Okay, so today's lecture I will be guided by, of course, I've introduced you to transpose, symmetric, diagonal, all of that, and I've also walked you through the basic calculations. Of course, the focus today will be that objective number 3, matrix decomposition, and where we're going to talk about the eigenvalue, the Koleski, the singular value, the QR, and so on like that. Okay, so let's get started. Want to decompose, want to be able to learn, you want to acquire mathematical skill of decomposing a matrix, because we believe when matrices are decomposed into simpler matrices, of course, we'll be able to understand, the data structure in a way. For you to be able to understand data structure at time, it requires simplification. And one of the way to simplify that is through you go through the matrix of decomposition. Okay, so just like what I said, when you have a matrix, how can we decompose that, into two or more simpler matrices? If I can multiply matrices, if I can combine matrices, of course, I should be able to split a matrix. Okay, so now, of course, they are very useful in so many ways, like solving system of equations, obtaining low rank approximation, and finding important features. Finding important features at times we're dealing with variable selection or something that has to do with the reduction, dimensionality reduction, where you got a lot of variables and you actually want to settle for few important ones that explain the largest variance in the data. Of course, one of the techniques that we use for that is principal component analysis, and of course, the principal component analysis rely on eigenvalue decomposition. Okay, so like I said, because of the fact that the statistical method relies on this kind of matrix decomposition like eigenvalue decomposition, Koleski, singular value decomposition, QR decomposition. I'm actually going to walk you through the basic fundamentals. How do we do this mathematically? Now, I'm going to start with the eigenvalue decomposition. Okay, in the eigenvalue decomposition, I need you to pay attention. Okay, we want to start with a matrix. If you look at equation 10 now, we actually want to start with a matrix A. Okay, so we take a look at a matrix A. A matrix A has an element. It's a square matrix. It's n by n, and by eigenvalue decomposition, we're actually going to decompose that into three simpler matrices. Okay, now let's have some understanding of the components of this. If you take a look at the first one, okay, that is the eigenvector. Okay, if you take a look at the last one here, of course, that is like the transpose of eigenvector, and of course, what you have in the middle is eigenvalue. Okay, eigenvalue is going to be what we have in the middle, and it is a diagonal. Okay, the lambda 1 up to lambda n. The lambda 1 will be it may be the variance. In the case of principal component analysis, the variance of the first principal component is the lambda 1. The variance of the second principal component is the lambda 2. By the time we start principal component analysis, of course, you actually going to understand that. But what I want you to know right now is by eigenvalue decomposition, if you have a matrix, we're actually going to decompose it into three. Okay, and the components of the three matrices, each of that, what they represent, is what I'm actually telling you, what I'm giving you here. Okay, and you know what? If you pay attention to the the one of the parts, like if you take a look at this guy, cis 1 is the transpose of the other. I expect that when I multiply the two together, it should give me identity. Okay, you remember yesterday I actually show you an identity matrix. Okay, so in the eigenvalue decomposition, okay, if I really want to know if I've already decomposed this using the eigenvalue one decomposition approach, then I can investigate for orthogonality. And the matrix is said to be orthogonal if I multiply the simpler matrix by its inverse and it gives identity. Is there any question on this page before I move to the next page? Is there any question on this page before moving to the next page? Okay, so if there's no question, I'm actually going to move to the next page. Now, in the next page, where we're talking about decomposition of matrix. Okay, we can split it into three. We can split it into two. Okay, but the eigenvalue decomposition requires that it should be split into three. Why? I'm moving from there to another decomposition that we call Koleski. So Koleski is we're actually going to partition it into two. We're going to split the matrix. We're going to decompose the matrix into two in such a way that I wanted to take a look at what is going on. L here is a lower triangular. What do I mean by lower triangular? It means after the diagonal, I'm going to draw something now. Give me 1 second. This is the diagonal, right? Then you're going to see this guy here, they fall in the lower part, right? And I'm actually going to call that it's going to be in form of a triangle. Can you see that? It's in form of a triangle. That's why it is called a lower triangular matrix. In a lower triangular matrix, you actually, after the diagonal in the lower part, you're going to see some element, but in the upper part has to be zeros. Do you see the upper part? The upper part has to be zeros. This is what we call a lower triangular matrix. And you know what? This is the whole of this is L. There's the transpose. You're going to find the transpose of that. So, which means by Cholesky decomposition, decompose matrix into two smaller pieces. The first piece is a lower triangular matrix, and the second piece is a transpose of the lower triangular matrix. Is there a question on this? Okay. Now I'm actually going to move. Now, you've seen eigenvalue decomposition. You've seen Cholesky decomposition. Now we want to go into singular value decomposition. Okay, the singular value decomposition is very similar to eigenvalue decomposition because the two of them actually decompose a matrix into three smaller matrices, but the components, okay, of these smaller matrices are not the same, because when you take a look at what I'm actually having now, in the case of a singular value decomposition, okay, in the case of a singular value decomposition, okay, if you take a look at that, the first component is a left singular vector, okay, and of course the one in the middle is the diagonal, okay, that we call the singular value. The singular value is in the middle, okay, and of course the V, okay, here we use the transpose of V, but the V itself is a right singular vector, okay. Now, but this is very, very useful in image compression, okay. By the time I walk you through image compression, maybe I have a picture, I have an image, and that very image, because of the storage, maybe because we do not have enough storage, and what we want to do is, can we have a way to reduce the image, to compress the image in such a way that it's not going to affect the quality of the image? Now, let me tell you this. When you have not done anything to the image, okay, the image is going to have a full rank, okay? But you know what we want to do? We actually want to reduce the rank, okay? Okay, they want to reduce the rank. Reducing an image is reducing the rank, okay? So, and that is why this is very, very essential in a low rank approximation, okay? But right now, what I'm just giving you, the information that I'm giving you is that, okay, when you talk about singular value decomposition, this is decomposing or splitting matrix into three smaller matrices in such a way that the first matrix is called the left singular vector, and of course the middle one is the singular value, and that is why it is called singular value decomposition. Okay, the middle one is the middle matrix is the singular value, and of course the other one is the right singular vector. And not only that, the condition of orthogonality must also hold. Okay, when I do u transpose multiplied by u, which is the left singular vector, and if I multiply the transpose of that with the original left singular vector, it should give me identity. And if I also do the same to the right singular vector, okay, I should also have identity. Okay, so I wanted to take note of that. Now, there are different kind of decomposition, and the choice of matrix decomposition will depend on your intention. Okay, as time goes on, you're actually going to see, you know, the area where this is actually where they are applied. Like for instance, when we start principal component analysis, so that actually relies on technique like eigenvalue decomposition or singular value decomposition and so on like that. So when they can look at the QR, of course, this is very, very useful in solving linear equation and so on like that. So don't forget, I said something the other time that matrix decomposition supports multivariate modeling. Not only multivariate modeling, it also supports statistical inference. Because if you want to actually conduct statistical inference, you are seeking for estimation of parameters, or you want to test hypotheses about parameter. So moving forward in estimating parameters, of course, you got no choice than to involve a matrix decomposition technique. So as time goes on, you're going to see all of this. But let me say this. The QOR decomposition, okay, split matrix into two, into Q and R, as you can see here, where Q is the orthogonal matrix, and R one is the upper triangular matrix. Of course, you all know why this is actually upper triangular matrix, because when I look at the diagonal, okay, now when you go to the upper part, okay, you have element, right, that form triangle. The lower part is all going to be 0. So this is an upper triangular matrix. So the QR decomposition, okay, decomposes the matrix into two smaller matrices. The first one is orthogonal matrix, and the second matrix, and the second one is the upper triangular matrix. Okay, I think I've walked you through the different kind of decomposition that we have, and what I want to walk you through now, what is the essence of matrix decomposition in statistical learning. I think I've already mentioned some. I said it's help in simplifying data structure, because multivariate data set, okay, if you have come across the multivariate data set, they're complicated in nature. And of course, the moment you convert them into matrices, and you can, decomposing that, will simplify, the data structure. Okay, but not only that, I also mention that maybe if you want to talk about reducing dimensionality, okay, maybe you have so many features. I have like 10,000 genes, and I only want to maybe just obtain 5 patterns out of 10,000 genes. Of course, I can go by way of dimensionality reduction. So, and the technique of reducing the dimension of a matrix actually rely on this kind of decomposition. Okay, I think I've mentioned that. I think there are still more. Okay, now let's take a look at that. I said dimensionality reduction, okay, and principal component analysis actually use the idea of a singular value decomposition, okay, to reduce the dimensionality. Okay, now we're going to one of the topic in this course is principal component analysis. So by the time we start the principal component analysis, you're actually going to see singular value decomposition taking a center stage. Okay, but I'm just trying to give you information right now, okay, in case we have so many features and we want to reduce the dimension, okay. One of the way to do that, while preserving, it's just like while preserving the variance, okay, is actually to use one of the technique of matrix decomposition. Now, number two is data compression. I think I mentioned maybe I want to compress an image. Okay, why do I want to compress an image? Every image has pieces, and of course, has dimension, and we have a storage issue. Okay, and how can we, the more the pieces, the more the dimension, is there a way we can actually compress, the image in such a way that we're never going to have a significant loss of information? What I mean by significant loss of information is, a way that we can still preserve the quality of the image, even though we're going to lose some information, but not going to affect the quality. Okay, that's what we call data compression. Okay, data compression. So one of the technique used in data compression is what splitting matrix. Okay, decomposing matrix, and of course here in data compression, we can use the SVD, the singular value decomposition. We can use a QR decomposition. Okay, any of that can be used. Now, another essence of decomposing matrix, okay, in statistical learning is noise filtering and signal extraction. I'm actually going to explain this. We want to believe. Okay, let me start from here. We find ourselves in a world where we actually want to understand our environment. We want to understand our political environment. We want to understand our medical environment. We actually want to understand our environment in general. Now, for us to be able to have, or to understand our environment, we need knowledge. Where would the knowledge come from? The knowledge is going to come from information that we got. Where would the information come from? Information is going to come from data. And let me tell you this. It means when we collect our data set, okay, information are hidden in data set. Therefore, we need something to extract the information. Okay, now every data set is contaminated. I'm going to say that again. Every data set, okay, is contaminated. Okay, when something is contaminated, okay, then you need filtering. You want to filter out the noise. The noise is going to be unexplained, and you want to extract the signal. The signal is the deterministic part of a model. It's more or less like you have a model specified. A model is going to be a combination of a deterministic and a random part. The random part is unexplained. The systematical part is the explain. Your model is never going to give you an exact characterization of reality, because in any specification of model, there's always going to be error. There's always going to be placed on random. Okay, and that is the reason why when you look at your data set, it's complicated, okay? And you actually want to extract signal. You also want to filter out the noise. Then you actually need to go by way of decomposition. Okay? It's like decomposing something that is contaminated into explain and unexplained. So the explain is the signal extraction. The unexplained is the noise. We always want to filter out the noise. Okay? So, and that's why I said by separating signal from the noise, okay, then the technique like SVD can actually do that. Okay, another one is latent factor discovery. As time goes on, we got a lot of techniques that we call non-negative matrix factorization. The non-negative matrix factorization. Okay, let me say this. Okay, do you know that decomposing matrix is similar to factorizing matrix? Okay, decomposing matrix is similar to factorizing. Okay, now take a look at this. If in algebra, if I have x squared minus y squared, okay, and I want to factorize that, that's going to give me this and this, right? What have I done? I've factorized this to give me this. Okay, now there's something that we call, one of the techniques of matrix decomposition is what we call non-negative matrix factorization. Why is it called non-negative? We're just trying to say the matrices that we're going to end up with, they have to be non-negative. Okay, now in factor analysis, in this course we're still going to do a topic called factor analysis. For instance, relationship exists among variables, but can we have a way to extract unobservable factors that could explain reason why they are correlated in the first place? Okay, so of course, different technique of matrix decomposition can actually be used to figure it out. So factor analysis also has to do, we use the technique of matrix decomposition. Okay, and also I said technique like non-negative factorization uncover latent factors. Okay, enabling interpretability. Let me tell you this: if you're able to extract, or if you're able to uncover unobserved factors, unobserved factors, that will enhance interpretability. Okay, in statistical framework where we seek explanatory goal, at times interpretability could be an issue. Okay, how can we make our model to be more interpretable? Okay, so we can go through all of that. Now, clustering and community detection. Okay, as part of the topic you're going to do, there's something that we call clustering, where we classify objects into clusters. Okay, objects that will belong to a clusters, of course, they have to be similar. Okay, so we have a technique that it's more or less like you have an heterogeneous population and you are now subdividing them. That's a splitting. So since your data set is multivariate in nature and can be written in terms of matrix, okay, achieving that, of course, you can actually split it. Okay, so that's what it means. So here I said the spectral clustering uses single values and eigenvectors, from matrix decomposition of the Laplacian matrix to identify clusters. So if I want to identify clusters, of course, I can actually do that. Then in recommender system, okay, I don't think we're gonna do this in this course, but I remember in one of the courses that I've taught before, statistical learning 2, situation whereby you have some set of movies and you have some set of individuals that watch movies, and probably I think that was a competition then organized by Netflix. So in their data, some data are missing because let me write this. Maybe we have user that I'm going to say customers, okay, and movie, okay, and movie, okay, movie A, B, C, D. Okay. Now, and maybe I have a user, let me say George, I'm just assuming. Okay, Kazim, I'm just assuming. Okay, Aliyah, and so on like that. Okay, if these are the customers, now they want them to rank the movie, because before they can, the NFD can recommend. That's what I call recommender system. Before they can recommend movie, so they actually want to hear, they want to see the way those who have watched the movies, the way they're going to rate the movie. Okay, now let's say George only watched movie A, C, and D. Okay, now this one is going to be missing. Okay, we're actually going to have, some spots that they're going to be missing, and when they are missing, okay, statistical method, okay, that you're going to use on data set require complete data set. If the data set are not complete and you have a problem of missing values, then we need to find a way to impute the missing value. Does that make sense? And you know what? One of the way to input missing value, to compute missing value, is to go by way of matrix decomposition. Okay, and remember the SVD can actually handle the singular value decomposition, can undo missing value, then alternative, least square, and so on like that can undo. We call that matrix completion, because initially the matrix was not complete, and there's no way, we're actually going to move forward, in the analysis, because our technique require complete data set, and because of that, then we need to be able to, impute the missing value. So what I'm trying to say, the matrix completion rely on matrix factorization or decomposition. Okay, so optimization in machine learning, of course, in machine learning, where maybe the objective is to minimize a function or to maximize a function. Of course, the idea of a matrix decomposition take a center stage, and that was why I said the method like Koleski decomposition and QR subsystem of linear equation that are critical for optimization algorithm in regression and classification. So, like I said, as time goes on, you're actually going to see that the matrix decomposition techniques here will feature in some of conducting. Okay, so another important essence of the matrix decomposition is in graphical models. Okay, so graphical models is a way like we use whereby we have a lot of random variables, and we believe that some of them are connected, some of them are conditionally dependent, and some are conditionally independent. And we actually use network, okay, and we figure out the probabilistic relationship among them. So I'm going to say the idea of a Higgins decomposition actually going to take a center stage in understanding the structural properties of the graph, because we're going to make use of a graphical graphical theory and a probability theory. Okay, so how do we understand the structure of the graph, like the clusters and so on like that? The idea of matrix decomposition is actually going to take a center stage. Okay, so what have we done today, and what have we done this week in general? I'm actually going to review what we've done this week. Of course, what we've done this week, I remember I introduced you to multivariate analysis, and of course, I also started what I call the linear algebra, because the linear algebra very, very useful in multivariate analysis. Okay, so it's like what we're doing this week. It's a little bit of introduction and trying to have a recap on, algebraic knowledge. Okay, I told you the other time, we live in a mathematical world, and we understanding of the world require that we live this world mathematically. So how can we live the world mathematically? Is just to have some mathematical knowledge, okay? And of course, you know what we're looking for, right? We really want to bring out information from a complicated, multivariate data set. And how are we going to achieve that? We have to go mathematical. We have to go mathematical in doing that because we want to analyze that. Analyzing data is, is a way. It's like we are transforming data. We are splitting matrices. We're doing all sort of manipulation with data set. For you to be able to successfully manipulate your data will requires certain mathematical knowledge. And that is the reason why we've been trying to review the fundamentals principle of linear algebra. Okay, so just like I think I mentioned that you also need to attach a material. Okay, this one. Okay, and I call miscellaneous. There are some other things that you can actually you need to review, okay, because the material also has to do with arrow codes, okay, because I know that it may be kind of it may not be visible to work with multivariate data manually. It's going to take forever, and that's why you need a code, okay, the arrow code. So I will advise that you go through this material, okay, to have understanding on some. Or let me do this. I think I still have some minutes. Okay, I have some minutes. Let me quickly go over this material. So I still have some minutes. Okay, I call it miscellaneous topics. Of course, it covers all what we've done, but except some little addition that you've had about. So let me start from here. Quadratic functions. Okay, do you know that from multiplying matrices together, we actually combination of matrices and vector is going to give us a quadratic function. Okay, now I'm going to say quadratic form. I have a matrix A, is symmetric in nature. Okay, so this is A. Then I have a vector X. Okay, take a look at the S prime. Okay, that's a row vector X. That's a column vector. Okay, then I'm multiplying. You can see the one I put in the middle. I'm actually going to call the matrix A maybe a constant matrix. And when I have X and another X, multiplying X by X, okay, in high school, that's like an X square, right? That's a quadratic function. But here we're going to call this a quadratic form. Okay, now this is how we form a quadratic form. Okay, now when we have a quadratic form, okay, quadratic form, if it is greater than 0, we're going to call that positive definite, because as time goes on, we're going to make use of this in one of the topics. Okay, so what I'm trying to say is that when you multiply all of this and you get this, now the result that we have is going to be a scalar. Okay, it's not going to be a matrix, and the result could be greater than 0, could be less than 0. So if it is greater than 0 means if it is strictly strictly positive. That's why I call positive definite, because greater than 0. Then you could have a situation where it be greater or equal to 0, possibility of 0. That is still positive, but we're going to call that semi-positive definite. If it can be less than 0, negative definite, less or equal to 0, negative semi-definite. So what we're just trying to talk about here is that a quadratic form, could be any of these four, depending on whether it is greater than 0, it is less than 0, or less or equal to 0, or greater or equal to 0. Okay, so here's an example. We have a matrix A. Okay, now if you're given this matrix A, now let me tell you this, please pay attention. you're only going to be given the matrix of constants A. X is just x1, x2. Why do I have x1, x2? Because the dimension of this matrix is 2 by 2. If it is 3 by 3, I'm going to have x1, x2, x3. Does that make sense? Because it has to be a square matrix. 2 by 2, okay, 3 by 3, 4 by 4, and so on like that. Now, at the end of the day, look at, oh my God, take a look at what I have. Let me see. If you take a look at what I have here, okay, this is going to be, because you have square, 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 okay, that will be positive, or 0. That was why you see greater or equal to 0, okay? So I just wanted to take note of that, because when you can be given, I'm seeing some assignment here. You're given a matrix, and they want you to obtain a quadratic form, and they want you to comment on the nature of the quadratic form, whether it is positive definite or semi-positive definite or negative definite or semi-negative definite. Okay? Okay, so these are the properties of definiteness. Okay? This is just trying to look at the eigenvalue situation where you have a quadratic form. What is the implication to eigenvalue